Welcome to another module in this massive open online course. So, we are looking at example problems in the discrete Fourier transform and inverse discrete Fourier transform, alright. So, we are looking at example problems for the discrete Fourier transform. In particular, what we would like to explore is we would like to write this DFT, the discrete Fourier transform, and the IDFT in a matrix form. That will be in particular very convenient for evaluating the DFT and IDFT as well as representing them as linear transformations. Okay. All right. So, what we want to do is, given x bar, the finite length signal, that is x0, x1 up to xn minus 1, and well, you can see this is the n samples, correct. So, these are n cross 1 vector corresponds to n samples, okay, n length signal. And we also have correspondingly x bar, which is the vector of DFT coefficients, that is we have naturally n DFT coefficients x0, x1, xn minus 1. This is your vector of DFT coefficients, and what we want to do is we want to express the DFT x bar equals vector w, in fact n corresponding to the n length DFT x bar, and also x bar the signal as the inverse DFT of length n times x bar. Okay. So, this expresses these things as a transformation. So, these are the matrix, this is called the DFT matrix, and this is the IDFT matrix, the inverse transform. So, we are representing the DFT and IDFT as linear transformations. Okay. So, these are basically your linear representing the DFT and IDFT as linear transformation. Now, the DFT, realize the DFT is given as well, the endpoint DFT summation n equal to 0 to n minus 1 xn into wn raised to the power kn. So, for instance, you have your x0, which is x0 plus x1 plus so on xn minus 1 into xn minus 1, that is it, wn raised to k is 0. So, this will be 1, and similarly if you look at x1, okay, x1 will be again x0 plus x1 times wn, k equals 1, n equals 1. So, plus wn plus x2 wn, well k equals 1, n equals 2. So, wn square plus xn minus 1 wn raised to n minus 1. Okay. This is x1. x2 will be, you can see, x0 plus x1, k equals 2. So, wn square plus 2, k equals to n equals 2. So, Wn 4 plus x n minus 1 Wn raised to 2n minus 1 and so on, correct. And so on. What we are trying to do is we are trying to develop a linear transformation, that is a matrix representation for this DFT. And if you look at x of n minus 1, that is the nth DFT point, that is going to be x 0 plus x 1, k equals n minus 1. So, Wn k minus 1 plus x 2, I am sorry, x Wn n minus 1, x 2 Wn twice of n minus 1 plus x n minus 1, k equals n minus 1, n equals n minus 1. So, that will be Wn raised to n minus 1 square. Okay. And you put all these things together as a matrix. So, you write in matrix form and what you are going to have is you are going to have on the left you have this n dimensional vector of DFT coefficients x 0, x 1 up to capital X 0, these are the capital X's, okay. These are the n dimensional DFT coefficients, this is this matrix, correct. 1 1, the first will be all ones, 1 times x 0. So, you look at this into what is multiplying each element of the signal. You look at what is multiplying each component of the signal. So, first entries will all be 1, 1 times x 0 plus 1 times x 1, so on up to 1 times x 2 plus so on 1 times x n minus 1. x 1 will be 1 times x 0 plus W n times x 1 plus W n square times x 2 plus W n raised to n minus 1 times x n minus 1. x 2 will be 1 times x 0 plus W n square times x 2 plus W n square times x 1 plus W n 4 times x 2 plus W n raised to 2 n minus 1 times x n minus 1, and the last entry, last row will be x n minus 1 will be W n raised to n minus 1 times x 1, W n raised to 2 n minus 1 times x 2 and W n raised to n minus 1 square times n minus 1 square times x n minus 1. And therefore, if you look at this, this is an n cross 1 vector, and if you look at this, this is an n cross n matrix, and this is your DFT matrix of size n, where recall W n equals e raised to minus j 2 pi over n, and this is your n cross 1 this is your n cross 1 signal vector, and this capital X bar, this is the n cross 1 DFT vector. So, this is your x bar, this is your W n, and this is your x bar. So, we are able to write x bar equals W n times x bar, okay, where W n is basically your DFT matrix. Okay. So, that is basically the structure of the DFT matrix. Now, you can do similarly for the IDFT matrix. Now, realize that the inverse discrete Fourier transform is also given as, if you look at each coefficient x of k, if you look at each coefficient, we have the expression for the IDFT x n, or I am sorry, x small n equals 1 over capital N summation k equal to 0 to n minus 1 x k w n raised to minus k n, okay, e raised to j 2 pi k small n over capital N, okay, w n raised to minus k n, which is also, as I said, this is 1 over n summation k equals 0 to n minus 1 x k e raised to j 2 pi k small n over capital. Okay. And now you can again write this as the following matrix. Now the outputs will be the signal samples, the inverse DFT. And the corresponding IDFT matrix. First you have the scaling factor 1 over n, that is there, and the input will be the DFT coefficients x0, x1 up to xn minus 1, and the IDFT matrix will be 1 1 1 1, that is small x0 equals capital X0 plus capital X1 plus capital X minus 1 divided by capital N. Small x1 is 1 plus Wn to the power minus 1 into capital X1, Wn to the power minus 2 into capital X2 plus Wn to the power minus n minus 1 into capital Xn minus 1. Similarly, x2 is, and overall divided by 1 divided by capital N, okay, and capital X2 or small x2 will be 1 over n times 1 capital X0 Wn minus 2 capital X1 Wn minus 4 capital X2 Wn minus 2 n minus 1 capital Xn minus 1, and finally xn minus 1 will be 1 over n times 1 capital X0 Wn minus n minus 1 capital X1 Wn minus 2 n minus 1 capital X2 plus and so on Wn minus n minus 1 square times capital Xn minus 1. And if you look at this, now this is, in fact this including the scaling factor 1 over n, this is Wn tilde. This is your n cross n IDFT matrix, okay, and this is your n cross 1 DFT coefficient vector x bar, okay. The input is the DFT vector and the output is the n cross 1 signal vector, and you can see therefore that I can write this x bar equals Wn tilde times x bar, and if you call this equation 2 and you call this equation 1, it is but natural to see that you have x bar equals, now from 1 and 2 equals Wn tilde into x bar equals, now substitute for x bar, capital X bar from 1, that is Wn tilde into Wn into small x bar. So, we have x bar equals Wn tilde into Wn into x bar. This implies that Wn tilde into Wn equals identity, must be equal to identity, right, correct. You have x bar equals, so you have the matrix x bar, the vector remaining unchanged, x bar equals a x bar, and that happens for every vector x bar. Okay, remember, it is not specific to a certain vector x bar, happens for every vector x bar, which means that the matrix A must be identity, alright, which means Wn tilde is the inverse of Wn. Similarly, Wn is the inverse of Wn tilde, and that is what, and that is natural, correct, because IDFT is the inverse of the DFT, the DFT is the inverse of the IDFT. Okay. So, therefore, Wn tilde Wn equals identity, similarly Wn into Wn tilde equals identity. The inverse of a square matrix when it exists is unique and is both, that is, if A B is identity for square matrices, then B A is also identity. Okay. So, Wn tilde Wn tilde equals identity. The DFT properties, DFT and IDFT properties matrices satisfy this property. Okay. So, this implies Wn equals Wn tilde inverse, and this also implies Wn tilde equals Wn inverse. Okay. So, DFT and IDFT matrices satisfy these properties, and further observe something very interesting. If you observe this, you can see that if you look at the elements, look at this. This is, if you look at the DFT matrix, this is the element. If you look at Wn, the element in the second row, third column is Wn square, which is also the element in the third row, second column. Look at this, that is Wn square, correct. Similarly, you can compare that Wn of I comma j equals Wn of j comma I for all j. You can see that. This means that if you take the transpose of this matrix Wn, it is equal to itself, correct, because Wn I comma j is equal, that is Wn I comma j equals Wn j comma I. If you make the rows into columns and the columns into rows, then the matrix remains unchanged, which means that the DFT matrix is equal to the transpose of itself. Okay. So, there is an interesting property, Wn equals Wn transpose. Okay, this is an important property. So, observe that. So, property, this is property 1, let us call this property 1, the inverse property, and property 2 equals, is basically Wn equals Wn transpose, and similarly you can also observe, if you look at the IDFT matrix, once again you can see that Wn tilde, for instance, if you look at Wn tilde of 2 comma 3, second row third column, that is Wn raised to minus 2 divided by n, and Wn tilde of 3 comma 2 is Wn raised to minus 2 divided by n. So, we again have Wn tilde of I comma j equals Wn tilde of j comma I. This implies Wn tilde equals Wn tilde transpose. Okay. So, we have Wn tilde equals Wn tilde transpose, and now we come to another very interesting property. If you look at this, each element, now you look at Wn of 2 comma 3, okay, that is Wn square, alright, that is e raised to j, that is Wn square, that is e raised to j 2 pi into 2 over n, that is e raised to j 4 pi over n. Now, if you look at Wn tilde of 2 comma 3, that is Wn raised to minus 2 divided by n, that is e raised to j 4 pi over n whole divided by n. So, you can see that these elements are complex conjugates of each other. So, if you look at this, example. And these are interesting properties. So, what we have is Wn of 2 comma 3 equals Wn, this is the small Wn, this is the matrix Wn, this is Wn raised to 2 equals e raised to j 2 pi over n, 2 pi over n into 2, that is e raised to j 4 pi over n, I am sorry, e raised to minus j 4 pi over n. Now, Wn tilde, the matrix Wn tilde of 2 comma 3 equals 1 over n Wn raised to minus 2 equals 1 over n e raised to j 4 pi over n, which implies Wn tilde 2 comma 3 equals 1 over n Wn 2 comma 3 conjugate, and that is the interesting property. Okay. So, each element of the IDFT matrix is a corresponding conjugate of the element of the DFT matrix divided by capital N. So, you can say basically the entire matrix Wn tilde equals 1 over n Wn conjugate, and this is the interesting property. And since Wn conjugate, Wn is Wn Hermitian, so you can also say this is also 1 over n Wn transpose conjugate, which is the same as 1 over n Wn Hermitian. Remember, if you take the transpose and the conjugate, that is, if we take the conjugate, that is the conjugate of each element, transpose, rows become columns, columns become rows. If we take transpose and conjugate of each element, that becomes the Hermitian. So, what you have is Wn tilde is 1 over n times Wn Hermitian. Okay. And therefore, since Wn tilde, so this is your property, you can collectively call this as property 3, and therefore, now you come to property 4, which is basically Wn tilde into Wn equals identity, n cross n identity. This implies that now you see Wn tilde is 1 over n Wn Hermitian, which means 1 over n Wn Hermitian Wn equals identity, which implies Wn Hermitian into Wn equals n times identity matrix. Okay, and this is your property number 4, that is Wn Hermitian into Wn is n times identity matrix. Okay, this is an n cross n identity matrix. Okay. This is an n cross n identity matrix. Okay. So, basically you can also say Wn inverse equals 1 over n Wn Hermitian, which is also basically 1 over n Wn conjugate, because Wn is Wn the transpose of itself. So, this is 1 over n Wn conjugate. This is also another way to say the same relation. Now, what we want to do is we want to write what the DFT and IDFT matrices look, n equal to 4 DFT comma IDFT matrices. That is, to get a better idea, what we want to do is we want to do a simple example where we write the DFT and IDFT matrices for n is equal to 4, that is the length of sequence n equal to 4. Now, realize that when n equal to 4, we have the W4, which is equal to e raised to j 2 pi over e raised to minus j 2 pi over n, e raised to minus j 2 pi over 4, that is e raised to minus j pi over 2, that is minus j. Okay. And now, if you look at this, if you look at Wn, so the matrix, just to distinguish this matrix, I am going to write it as W bar n to distinguish that this is a matrix, because Wn we are using it for the coefficient. This will be first, this will be n cross n, this will be 4 cross 4 matrix. Okay, so this will be a 4 cross 4 matrix, and the elements are going to be, first elements are all ones as we have seen. 1, this is Wn raised to 1, that is minus j, Wn raised to, the second 2 cross 2 element will be Wn square, that is minus j square, that is minus 1. Third element will be Wn cube, that is minus j cube, you can see that will be minus 1 into minus j, so that will be j. Okay. Similarly, this element, third row will be 1, again remember this is transpose symmetric, so I can just write it without looking at it. So, this is going to be minus 1, this element will be Wn raised to 4, so this will be minus j raised to 4, though that will be 1, and again this element will be Wn raised to, I think if I am not mistaken, Wn, this is k equal to 2, n equal to, this k equal to 2, n equal to 3, so Wn raised to 6, that will be minus 1. Okay. And the last row, again you can write it by transpose symmetry, this element will be j, because remember this is the 4 comma 2 element, that will be same as 2 comma 4 element. This element is 4 comma 3, that will be the same as 3 comma 4, and this element, last element, is Wn raised to n minus 1 square. So, that will be Wn raised to the power of 9. So, you can see that will be minus j, you can check this. Okay. So, this is basically your 4 cross 4 DFT matrix. Okay. Now, the IDFT matrix, in fact here n is equal to 4, let me call this Wn tilde, you can write this as 1 over 4, and remember to do the IDFT matrix I do not need to go through the entire computation once again, I can just consider the conjugate of the DFT matrix, that gives me the IDFT matrix. Okay. So, that is very simple. So, the IDFT matrix is indeed, once you have the DFT matrix, the IDFT matrix itself is very simple. So, that will be 1, 1, 1, 1, second row take the conjugate of each element, minus j conjugate is j, minus 1 conjugate is minus 1, j conjugate is minus j, third row will be 1, minus 1 conjugate is minus 1, 1 conjugate is 1, minus 1 conjugate is minus 1, last row will be 1, j conjugate will be minus j, minus 1 conjugate is minus 1, and minus j conjugate is j. Okay. And this will be your 4 cross 4 IDFT matrix. And where we have used the property Wn tilde equals 1 over n Wn conjugate, in this case specifically n is equal to 4. Okay. And now you can also verify that, yeah, and this is something that you can do by yourself, you can enter it into MATLAB and you can verify that Wn tilde into Wn is in fact identity, and you can also check that Wn Hermitian into Wn or W bar n, rather these are all W bar n, these are the matrices, W bar n Hermitian into W bar n, remember we said W bar n Hermitian, W bar n, this is equal to n times identity. Okay. So, you can check these things, you can verify these n times n cross n identity matrix. So, you can verify these properties. So, you can do this as homework, you can enter this into MATLAB. MATLAB gives a very convenient interface to enter matrices, so you can quickly enter these matrices and verify these properties. Alright, so in this module we have dealt with an important aspect, that is representing this IDFT and DFT operations as matrices, and this is a very important I would like to say tool, because it allows us to represent these operations as linear transforms and therefore look at these as matrices and use these tools to carry out these operations in analysis, right. So, representing the signals and outputs as vectors and representing these DFT and IDFT operations as matrices, okay, and that helps us significantly simplify analysis and represent it in a much more compact and sort of intuitive fashion. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.